of n, right? So that proves the theorem, so hence proven.
Hey guys, what's up? I hope you're doing great. In this video I'll be telling you about mathematical induction, which is used to prove theorems. It is a very important method of discrete maths. But before we move on, please make sure you've subscribed to my channel and hit the bell icon for notifications. Let's see what mathematical induction is. For example, we have a ladder in which you have steps, right? So mathematical induction works on the principle that, for example, there's a theorem P, it's a function of n, you can plug in different value in the place of n. So for example, it's a statement or a theorem, just as we saw in direct proofs or other proofing techniques. So P of 1 would indicate that our theorem is able to climb the first step of the ladder, first rung of the ladder or first step of the ladder. So where 1 is actually the base case, and then there is some arbitrary step which is the kth step. Let's say this is the kth step, this is the first step, this is the kth step or kth rung. The next rung is k plus 1, right? K plus 1th rung, right? So first we prove that our theorem is able to climb the first step, right? This is our check. If this check comes out okay, right, then we assume this part, this is our assumption, and based on this assumption we check whether that if, for example, this assumption is true, then is the k plus 1th thing also true? So we check this part. So if this is also true, if this is assumed true and this comes out to be true, then we say that this theorem is valid and this theorem is proven. So this is the process. So let me briefly describe it again. So we have a theorem which is called P of n. First we check it for the base case, normally 1. If that check is valid, we say that our base case or basis is proved. Then we assume that this theorem is valid for kth step. So this is just our assumption that it is true for kth step. We simply plug in instead of n a k. It's a simple substitution step. When we do that, then we see that if this thing is true, can we reach from p of k plus 1 to p of k, which was our original truth. So if p of k plus 1 comes out to be true based on previous assumption, then we say that this theorem holds and this theorem is true. From a ladder point of view, you are saying that your theorem is able to climb the first ladder, and for k and k plus 1 you can go from one step to the other step. So if every step is identical, so you'll be able to go from the previous step to the next step. That means that this theorem is valid for all the values of n, right? So this is mathematical induction. So the formal statement for this proving technique is that this is the if part. If p of 1 is true and for all k, if p of k, then p of k plus 1 is true, then if all of this is true, stating that the base case is true, and for all k, if p of k, then p of k plus 1 is all, if all of this is true, then it says that our theorem is proven for all n p of n. But obviously this complete thing is for the proofing technique, but this part is actual proof of the theorem, right? If we say that this is true, then obviously this technique is also true. So let's do an example before we go on to some problems for this part. So let's do an example. The example is, for example, you have summation series 1 plus 2 plus 3 up to plus n. We claim, the theorem claims that it is equal to n into n plus 1 divided by 2. We saw this in the previous video, that series are can be constructed using summations, and there in order to evaluate the series you can expand it and add the terms manually, or you could use a formula. So this was a formula that we saw in the previous video. You can check this out if you go to the playlist Discrete Maths. So there are two steps, right? So the technique says that there is first the basis step and then there is the inductive step. So in order to use the mathematical induction, you have to do both of these things, that you need to do the basis step, prove the basis step, and then go to the inductive step, right? So let's first do the basis step. In order to prove the basis step, and by the way, let me make this clear here that all of this thing is p of n, right? So this is the point where most students get a little bit confused. What would be p of 1, right? P of 1 for all of this statement would be as if the n was equal to 1. So for example, n is equal to 1, the right hand side is easy, you simply substitute 1 instead of in place of n. But what about this part, right? If I went on doing 1 plus 2 plus 3 plus so on up to 1, right? What is this? It's not going anywhere, right? It's really illogical to do that. But although you have just done the substitution of 1 in place of n, but that is wrong. Why? Because the series doesn't work in this way. The series is actually something which indicates that there are n terms in the series. So if there are n terms in the series, that means and if the value of n is 1 by chance, you are saying that there is only one term on the left hand side, right? So I am actually going to point this here. There is only one term on the left hand side because n is equal to 1, and p of n indicated that there are n terms. P of 1 would indicate that there is only one term. So make that really clear in your mind, right? Good. So on the right hand side, you substitute in place of n a 1, so, right, divided by 2. So 1 is equal to 1 into 2 divided by 2, which is equal to 1. So you can say here that the left hand side is equal to the right hand side. That means the basis step is true. Then what did we say earlier? You first have to assume that for the kth step this theorem is true, right? So let's just assume that. So this is the second step called the inductive step, and in inductive step you simply write p of k and assume that it is true, because we have seen that p of 1 is true. That means p of k can also be true, right? So p of k will be simply all of that thing written in terms of k into k plus 1 divided by 2. So this will be our kth assumption. Now what about k plus 1? So we are saying that the theorem is true for kth step. For k plus first step, this theorem will have to be written using the theorem for k plus first step, and then we are going to find p of k inside of that so that we can judge its validity, right? So p of k plus 1 based on p of k would be 1 plus 2 plus 3 plus so on. Now we are simply using substitution here. We are not adding anything to it or doing anything like that, right? Just substitution. Instead of n, now we are writing k plus 1. You can verify this if I am doing it right. Plus 1 divided by 2. This is our kth step. We have assumed that this is true for kth step. This is just our assumption. Now we will be checking if we can go from kth step to k plus first step, right? So what we do is we start from the kth step and we try to climb the next rung of the ladder. So p of k was 1 plus 2 plus 3 plus and so on plus k equal to k into k plus 1 divided by 2. So what if we used this assumption and went on to the next step? Let's do that. 1 plus 2 plus 3 plus so on up to k. So adding a new term would mean adding this term on both sides. Now our objective is that we want to prove this equation, let's call it equation B, equal to equation A. If A and B becomes equal, then we say that the theorem is proven, right? So starting from B, now we solve this. The left hand side will remain just like this, but the right hand side, so this is k into k plus 1 plus 2 into k plus 1 divided by 2, which is equal to, so you can take k plus 1 common and you will get k plus 2 divided by 2. So if you go and see the right hand side of A, you can I'm just going to rewrite the right hand side of A as k plus 1 into, add these two ones, so we'll get k plus 2 divided by 2. So now you see all of this P of k plus 1, which was an independent statement, is exactly the same as this statement, which was started from P of k. So we have two independent things. One was P of k, one was P of k plus 1. These were based on the assumption that P of 1 is true. But then we started from P of k and went towards P of k plus 1, and we were able to do that. We were able to reach P of k plus 1. So for theorems which are already proven and known to be true, we can use this technique to reassure that they are true. So you'll get the same kind of problems in textbooks, and they'll be asking you to do that. But this technique doesn't really, it's a mechanical kind of technique. It doesn't really provide any insight about the theorem, that whether it can be proven to be not true. So you just try to reach a point where it is shown to be true, right? Mostly when it is already known that it is true. I hope you understood this concept, and I hope you liked the video. So if you did like the video, please press like, and if you haven't subscribed to the channel yet, please do subscribe. Thanks for watching.